let's start talking about these integrated rate laws in terms of the challenge problems. Okay, so if we look at the challenge problem, for today we have dinitrogen pentoxide decomposes in the gas phase to form nitrogen dioxide and oxygen gas. This reaction is first order and has, with respect to dinitrogen pentoxide, and has a half-life of 2.8 hours at 25 degrees Celsius. If we have a certain volume containing a pressure, what partial pressure will be present after 215 minutes? All right, so just because we can, let's write the balanced chemical equation, right? So we're doing a chemical equation where we have dinitrogen pentoxide, right, which is a gas, is decomposing to form nitrogen dioxide and O2, both as a gas. Right, so in order to balance this, we need a 2 there. Actually, to get an even number of oxygens, we're going to put a 2 on this side. So that means we need a 4 there. And in front of the oxygen, we need then, that's 8. That's right. So we have a balanced chemical reaction. All right, so we want to know information about this one after a certain amount of time. So then we have to realize how this is going to, the concentration is going to change per time, right? And it's going to depend in part on the type of reactions there are, right? So we can talk about something being 0 order. We can have a first order, and we can have a second order reaction, right? Let's move the first order. And from this, we can describe the changes, right? If we look at what's going to happen for what we call the integrated rate law, or the straight line form for a 0 order, we can say that the concentration of some species A after some time is equal to the rate constant lowercase k, excuse me, negative, times the amount of time that that reaction occurs, plus whatever concentration we had at the beginning. So when we do that, we can talk about then the half-life, how long it takes for this reaction to decrease by half is going to depend on the amount that was there at the beginning. So we can say that that is a 0 over 2 times the rate constant k. And what that really is going to do is if we graph the concentration of A versus time, we are going to get a straight line that does that, right? Where the slope is equal to a negative k. If we look at the first order, in a first order reaction, we can say that the natural log of concentration at some time t is equal to a negative 1, or excuse me, negative k times t plus the natural log of A initially. So we can talk about the time that this would take to get the half-life. Now it's independent of the initial concentration. So the half-life is equal to the natural log of 2 versus k, right? And we can do that by putting the fraction in both of these so that kt is 1/2 of A naught. Right? So what that means is when we graph this, now we're going to take the natural log of A versus time. We are going to get a straight line with the slope, again, equal a negative k. And finally, we can look at the second order. And we can say that now the concentrate 1 over the concentration after some time is equal to the rate constant KT plus 1 over the concentration initially, where in this case our T1/2, our half-life, is equal to 1 over the rate constant K times A naught. And when we graph this one, it's going to be 1 over concentration of A versus time. And we are now going to get a straight line that does that. And the slope is going to be equal to K. So this is the integrated rate loss for the 0, the first, and the second order, right? We in this problem are saying we're told that this is a first order reaction, right? So we're going to be using this, right? So we can describe the concentration at some time t as being or the concentration changing using this first order rate equation. Right? So that's going to be, in this case, it's going to be the natural log of the concentration of N2O5 at some time t is going to be equal to the negative KT plus the natural log of the concentration of N2O5 initially. So this is, if we want to know this concentration, we need to know all of this, right? Well, we know the time, right? The time they give us, we want this reaction to go 215 minutes. Do we know the rate constant? From the information that we are given, do we know the rate constant? Well, we know that the half-life is 2.81 hours, right? And we know from down here that the half-life of a first order is the natural log of 2 over K. So if we know the half-life, we can calculate the rate constant. So if we know that T1/2 is equal to the natural log of 2 over K, therefore the rate constant lowercase k is equal to 1 natural log of 2 over T1/2, which is equal to the natural log of 2 over 2.81 hours. So this is equal to, if we convert, because this time is in minutes, we need to convert this to minutes. So if we do that conversion down here, there's 1 hour is 60 minutes. Now our rate constant is 4.111 times 10 to the, can't read my own handwriting, -3 minutes to the -1. So now we have the rate constant, we have the time. The only thing now we need is the initial concentration. Right? So we have again, these are in concentrations, we have a gas, so we can convert to, when we have a gas, we can say PV equals nRT, right? If we want a concentration is moles divided by volume, right? So from this equation, that means we have P over RT, right? Which would be equal to the pressure of our gas, which was 745 torr, but we don't work this. R value isn't in torr, it's in atmospheres. So we have to convert 760 torr is 1 atmosphere. Right? Our gas constant is 0.08206 liters times atmospheres divided by Kelvin times mole. And our temperature, we said up here, was 25, which would be 298 K. So now that cancels with that, that cancels with that, that cancels with that. We're left with 1 over moles, or liters divided by moles, which will flip to the top. So our concentration initially is 0.04007 molar. Questions on any of that so far? So now we have the initial concentration, we have the rate constant, we have the time. We can then calculate the concentration after this time. Right? So the natural log of N2O5 after 215 minutes is equal to our rate constant, a negative 4.111 times 10 to the negative 3 minutes to the minus 1 times our time, 215 minutes, plus the natural log of our initial concentration, which is 0.04007 molar. So when we do that, this natural log of N2O5 at 215 seconds, or minutes, excuse me, is equal to a negative 4.101. Right? To get rid of this natural log, we have to raise this to the E. So the concentration of N2O5 at 215 minutes is equal to E to the negative 4.101, which is equal to 0.0165 molar. And if we just do a quick double check, this number is less than this number, right? Which it should be because the reaction's occurring. Okay. So, but that's not what the question asked, because that would be too easy, right? Then it would be an easy problem instead of a challenge problem. We want to know the partial pressure of O2. Right? Right now, we know the amount of N2O5 remaining, right? Which is horribly spelled. Actually, I spelled it right. I just can't read it. Remaining, right? So because we have this balanced equation, right, we can convert. If we figure out how much of the N2O5 reacted, that's going to be related to the amount of O2 that was formed. The amount of N2O5 reacted is equal to the concentration of N2O5 initially minus the concentration of N2O5 at the 215 minutes, which is going to be equal to the 0.400, or excuse me, 0.04007 molar minus the 0.01656 molar. So this value then is going to be 0.02351 molar of N2O5 reacted. Okay. So now essentially we have an indication of how many moles reacted. Right? So from our balanced chemical equation, if we have 0.02351 moles per liter of N2O5, right? From the balanced reaction, for every 2 moles of N2O5, we get 1 mole of O2. So then when we do that math, we end up with 0.01175 molar of O2. Okay, so now we're actually in terms of O2, but the problem, again, if we go back, doesn't want a concentration, it wants a partial pressure. So that means we have to use, again, PV equals, actually, let's change color again. We want PV equals nRT, right? Where now we want the pressure, which is nRT over V. If we look at this, that value is the molarity. So this was going to be P is equal to the concentration times RT, which is going to be equal to 0.01175 moles per liter, again, times our gas constant, 0.08206 liter atmosphere Kelvin mole. Now the moles cancel, the liters cancel, and our temperature, again, is still 298. Or Kelvins cancel, and we're left with a partial pressure of 0.288 atmospheres. And if we want to complete the circle, that is equal to 218.6 torr. Right. So then this is going to be the partial pressure of O2 that is formed in this reaction, right? Because of that process. Step back. Okay. And when I zoom out like that, you guys can't see it. All right. Any questions on that problem? It was kind of lengthy. We were actually able to calculate all of those.
Could you scroll back down to the last step, please? Thank you.
So again, we can look at these integrated rate laws as being a time-dependent equation, right? But we can also use these to determine or help determine orders experimentally, right? For example, when you do lab, when we do the kinetics lab in lab, which is a horrible statement, but when we do the kinetics lab, right, we're going to be monitoring concentrations with time, right? And then if we look at those in terms of graphing that concentration, right? If we graph the change in concentration versus time and get a straight line, we can say that that is zero order with respect to that. If we graph the natural log of the concentration versus time and get a straight line, it would be first order. If, on the other hand, we graph 1 over the concentration versus time and get a straight line, that would be second order. All right, so this is another method that we can use to follow concentrations and help determine rate laws or rate orders, right? But if you remember, all of this rate information has to be determined experimentally. Any questions on any of that? Any questions about anything? All right, then. Hearing none, let's go ahead and break into our groups and start working on these integrated rate law in-class activities.